Hello, everyone. And today we are doing another webinar on hydrostatics. Okay, so I hope people are joining. That's brilliant. Okay. I wonder what you see before you join. Do you see a welcome screen and some message? This will start soon. Is that what you see? Waiting for us to start. Okay, thank you. Yes, that makes sense. Right, so how do I... Okay, I am in Spotlight. Right, so... Oh no. Speaker. Okay, that makes sense. Excellent. So today we're talking about hydrostatics. I'm going to share my screen again. And I'm just going to share the screen as a normal. Okay, so I just need to open the chat. So chat. Chat is here. Okay. Is it possible to go through a problem similar to problem 8? Well, let's have a look at problem 8. It's good. Assignments, physics. What is problem 8? Oh, yes, I think. Did you ask me last week as well? How dimensions are needed for a long thin circulation with 1 liter of water? Okay, so right. Actually, yeah, let's start with that one. What you have here? What dimension needed if a long, thin circular tube filled with 1 liter can shatter a 50 glass flask at a video clip? Okay. I'll rephrase this. I'll ask a different question. One, what are the dimensions of a tube if 1 liter can make a column 300 meters tall. Okay. What are the dimensions of a tube if 1 liter of water can make a column 300 meters tall? Well, so we have, all we need is just a tube. So if it's a round tube, so it's a cylinder. Basically, it's a cylinder of water. Let's make it neater. It's a cylinder of water And we know that the pressure, so we know the height of the cylinder, and we know the cross-sectional area. We know that the cross-sectional area is pi r squared. And the volume, so the volume of a cylinder is A multiplied by H. So the volume is pi r squared H. Therefore, the volume is given. We know that the volume is 1 liter. So 1 liter is 0.001 cubic meters. That's 0.001 cubic meters. Pi r squared and multiplied by H, which is 300 meters. 300 meters. So r squared is 0.001 divided by pi multiplied by 300. So that's equal to 0.001 divided by 3.14 divided by 300. That gives us 1.06 times 10 to the minus 6 square meters squared, which is 1.06 millimeters squared. So that's the radius. So that's radius squared. So the radius is square root of 1.06, which gives us well, approximately 1.03 millimeters. So it's a tube of radius r equals 1.03 millimeters. So that's what you need to find. And the height, well, you need to work out yeah. So you have the pressure. So you want to know what is the pressure, and the pressure can be found using the formula rho gh. So use this formula to find h, and then you use that h to find the dimensions. Okay. Does that help, Rihanna? Okay. This is a similar question. Similar question. So you are trying to you have the volume, and you're searching for R. Which formula? Which formula are you talking about? Oh, this formula. So pressure at the bottom. So pressure is equal to density. Density multiplied by gravity, gravitational field strength. Gravitational field strength multiplied by the height. Okay. Right. Good. So problem one, derive the formula F equals rho GV. So this is the formula for the upthrust force. This is the formula for the Archimedes force. What is it? So if you have an object suspended in water, and the volume of the object, volume equals V. Density is the density of the liquid. So this object is inside a liquid, or inside a fluid, sorry. Inside a fluid, volume V. Fluid. Yes, these problems we are doing will help you with the entry test. So fluid density equals rho. and G is gravity. No, problem 1 does not help with problem 1 on the test. No, they're not related, but problem 1 is an explanation of this formula, right? So here I just went through problem 8 because yes, Pirana was asking. She was asking last week, 2 weeks ago. So I'm happy to help. Oh, what is the interest? The interest test is the first assignment. Yes. When you said you have to show your working out on paper quite a while, do you mean we should all do our working out on paper that we can do it on calculator, write down what we did? No, you can do it on a calculator, of course. You just say that. When I say working out, I mean this, yeah? I mean this. I'm not showing you, of course I'm using a calculator here. I'm not asking you to do it by hand, right? But it should be clear what you are doing and how. Yeah. An example of a bad of a not working out would be no working out at all, just the answer. So the formula F equals rho GV. So you have an object suspended inside a liquid, and it takes up volume V, and the fluid density is rho. The formula gives you the upthrust. So the upthrust is the force that the liquid or the fluid pushes up, and this force is the density of the liquid multiplied by the gravitational field strength and multiplied by the volume of the object. And that's important. This is the upthrust force. Upthrust force. So we are going to prove that formula. And I'll try to do this quickly. And so imagine we have an object of which is a cuboid. Actually, a cube. That would make life easier for us. Imagine the object is a cube, and it's suspended in a liquid. Right. So it's inside a liquid. And imagine that the top of the box is at a depth h. And A is the side of the box, A. So the bottom part of the box, what is the depth? If this is h, what is the depth of the bottom of the box? A plus h, very good. H plus A, right. So that the water pushes on the box from the top. So there's pressure from the top. And we know that the force is equal on the top is equal to the pressure on the top multiplied by the area. And the area is a squared multiplied by area, which is a squared. Okay, is everyone happy with that? The force is pressure times area. Force is pressure times area. So pressure is P top and area is a squared. And we know that the pressure is equal to density of the liquid, GH, rho GH. Okay, so the pressure is rho GH. So here the pressure is rho GH. So on the bottom, the pressure is different because the H is different. On the bottom, the pressure is rho G H plus A. Yes, because it's deeper. The bottom of the box is deeper, therefore there's a bigger pressure pushing it up. Now there's some pressure pushing on the sides, but it's equal in both directions. It's equal from the front and equal from the back, equal from the left and equal from the right. So these forces cancel out. So force on the top is pressure on the top times A squared, which is rho GH multiplied by A squared. The force on the bottom is the pressure on the bottom multiplied by A squared. And the pressure on the bottom is rho GH plus A multiplied by A squared. And the net force, because we know the upwards force is force on the bottom minus force on the top. Because if you have two forces, one pushing up, one pushing down, you need to subtract them, which gives you net force is equal to the bottom force. So it's rho G H plus A squared minus rho G H A. Now we open the brackets, a rho G H A squared. We open the brackets, and it's going to be rho G H A squared plus rho G H A cubed minus rho G H A squared. Rho G H A squared cancel, and we're left with, so the net force is equal to rho G H A cubed. But A cubed is the volume of the cube, which is rho. Sorry, I've done something wrong. There's no H here. Sorry. Rho G A cubed. Rho G A cubed. So it's rho G V. Rho is the density. Rho is density of the liquid. So the force on an object which is suspended in a fluid is rho GV, where rho is the density of the fluid, G is the gravitational field strength, and V is the volume. And this is the proof. So I suspended a proof, or a cube. Right. In your assignment, you have a similar proof, but it's for a cuboid. Slightly more complicated, but here it is. Now, if you don't fully understand it, it's not the end of the world, like honestly, because you can still use the result. You can still use the result that the upwards force. So if you jump into a bathtub or a swimming pool, the water pushes you up. And that force there's a formula. It's the density of the liquid multiplied by the gravity multiplied by your volume, the volume of your body, which is about, well, different people have a different volume, but typically is between 50, your volume in liters is approximately equal to your mass. Okay, so I am 75 kilograms, so I would be approximately 75 liters. So because my density is approximately 1,000 kilograms per cubic meter. Because I float. Yes, I just about float on the water. So that's how I know my volume. Of course, when I breathe in, my volume increases, and that's why I float better. When I exhale, I sink because my volume decreases. Anyways, problem 2. A bucket of water is on scales. A block of wood is placed into the water. So you have a bucket of water. And it's on scales, on an electronic balance. And the electronic balance shows you something. Let's say it tells you, I have another one. I'm quite pleased with that, so I'll do another one. So let's say our typical bucket of water is, I don't know, 9.6 kilogram. And you place a block of wood. You place a block of wood on top. What will the bucket, what will the scales show? Then does anyone know? We can, let's say the block of wood is of wood is 1.2 kilograms. It's a lot of wood, but anyways, what do you think? What do you think will happen? 10.8, yeah, correct. But do you have an explanation why? Because the wood is not touching the bucket, is it? Is it? Why? Increases the mass inside the container. True. But I'm still not convinced, because the block is not touching the bucket. Why would it increase? A force is exerted onto the water. That is right. So why is everyone doing direct messages? Don't do direct messages. Come on, it's a discussion. Discuss. Don't send messages. Increases the pressure. Ooh, Giselle, that's a very good one. Why does it increase the pressure? That's very good. The water will increase the pressure. How? Why does this happen? And Camille, well, but the block, because less space, the block down in the water. Equal and opposite to the force of upthrust. Well, that is true. Look, you're saying everything's you're saying the right things, but the pressure in a liquid is only dependent on the height of the fluid. Once again, the pressure in a liquid, pressure at the bottom, so pressure is the density of the water times G times height, where height is the depth of the bucket. Thank you, Dania. Yes, the height has increased because when you put the wood into the bucket, the water level has increased. Right? So the water level has increased in the bucket. It has to. And because it increased, the depth has increased. And so thus the pressure on the bottom has increased. The pressure on the bottom has increased, therefore the force on the scales have increased. Yes, so some of the water, the water level increased. So the pressure on the bottom has increased. Now this doesn't really help with the mass, but obviously we can do the calculation and say, well, that's the total. And this will help you with problem 14, by the way. This will help you with problem 14 because it's important. So for the first one, for the first bucket, you have the gravitational force, mg, where m is the mass of the water, mg, and up we have a normal reaction force. Normal reaction force, which is pushing here. Normal reaction force, n1. Let's call it n1. And this is the force that is being measured by the scales. So the mg is what? 9.6. So that's about 960 newtons. That means this is also about 960 newtons. And this is the force that is being measured. Now for the second bucket, you have the gravity of the water, so that's mg. Then you have the gravitational the force of the wood, and you have a normal reaction here. So you have mg, which is approximately 960 newtons. You have the m2g, that's the mass of the wood. So that's 1.2 kilograms. So it's about 12 newtons. Sorry, 96, of course, not 960, 96 newtons. And here's 96 newtons. And the upwards force is N2, is the normal reaction force here. So you can see that the normal reaction force is M2G plus mg. So that's 12 plus 96. So it has to be balanced. The upwards force has to be the same as the downwards force. So that's 108 newtons. So the reading on the scale, will be 10.8 kilograms, because 108 newtons is correspondent to 10.8 kilogram. If you want to find these, if you want to watch these again, you go to our website and you click webinars, and then year 10 webinar, playlist, year 10 YouTube playlist. And that takes you to the year 10 webinars. And you can also watch the year 12 if you wish. Like I don't always add them here because it just takes a long time to add them here, but you can just click the playlist, and that gives you all the webinars. Year 11 is the same as year 10. Sorry, so when I say year 10, I mean year 11 plus year 10. Basically, this is a year 10 course, but it is an advanced course, and we allow year 11s to do it, but a limited number of year 11s. Okay, so yeah, and you can see that N2, the normal reaction force here, is 108, so it's going to be more. Okay, I need to start calling them year 10, 11, but yeah. Problem 3. You are in a boat in a small lake. In the boat, you have a heavy object. If you throw the object into the water, would the water level in the lake change? Access the whiteboard. This is the whiteboard. Okay. Let's see. This is a lake. And let's say the water level is here. And you have your boat. You have your boat. This is you. And here's a heavy object. Okay. What do you think? It would change as it's not the mass without that matters. I'm not sure what you mean, Kizar, but let's look at this way. Let's imagine this is called extreme case analysis. Extreme case analysis. Extreme case. Suppose the object is very small, and very heavy. Now the boat would rise by as much as the heavy object displaces the water. The boat would rise. The boat would rise. What about the water level? The same water level should stay because the mass of the object in the water stayed the same. Water level, yeah, because the pressure just separates when in the water the thing displaces its volume. Lots of great ideas. When the boat is displaced water because of its mass, it will not be the volume which changes the water level, so it's checked into the water. Well, if you drop something into the water level increases, yes? Right. So let's say the rock is here. It's not in the boat. And we are right. So let's say the boat is out of the water. The boat is not in the water yet, and the object is not in the boat yet. So ooh, Vishaka. Yes, very good. That's a very good explanation. Yes, you are correct. Look, what happens when the boat is put into the water level rises. When you put the rock into the boat, the the boat goes even deeper. And the water level rises even more. Okay? But remember, the object is very small. The object is very small, but very heavy. Okay? So do you understand the sequence? So we have the boat is out of the water. We put the boat into the water level rises. Now we put a rock into the boat and the water level rises even more. Okay? Now the next picture, for the next picture, we've dropped the object is now in the water. And it doesn't displace any water because it's very, very small. It doesn't displace any water. And a small object, if you throw a small object into the water, that doesn't change the water level, does it? It just, well, it changes so small that it doesn't matter. And that means that the boat goes back up. And hence the water level drops. It actually drops to the same level as this one. So I'm just going to adjust it ever so slightly. And adjust it here. And this one, yeah, well, approximately like this. Okay. So for an object that sinks, the water, if the object sinks in the water, if conclusion, if the object sinks, and the water level will fall. The water level will drop. Water level will drop. It might as well not exist. Why? Well, if it's a very small object, yes, it's on the bottom of the lake. Now, the second case, if the object is lighter than water, what if the object floats? If the object floats. Well, here we need to understand that the weight of the weight of the floating object is equal to the weight of displaced. This is the Archimedes principle. Weight of the floating object, weight of weight of the displaced water. And that's that is important. So imagine now we do another extreme case, and the extreme case being that the boat is very, very light. Extreme case, the boat is super light. Extreme case, boat, suppose the boat is very, very light. That means it doesn't displace any water whatsoever. So you are out of the boat. The boat is out of the water. The boat is out of the water. And when you place the boat into the water, when you place the very, very light boat into the water, that does not change the level of the water because the boat is literally on top because it weighs nothing. It weighs nothing, so it's literally on top of the water. Imagine a styrofoam boat, like super light. So the water does not change. So just the boat itself does not change the level. Does not change the water level. Now you place yourself. You are an object that floats. So you place yourself into the boat. And of course, the boat sinks and the water level rises. You place yourself. Water level rises. And the extra water level, and that's important to understand, the change in the extra water Interesting. Yeah. The extra water, this bit, and this bit, is equal to your weight, the extra weight of extra water. Weight of displaced water. Well, not extra, it's displaced. Weight of displaced water is equal to the weight of you. Yes, of yourself. Yes. And therefore, when you jump out of the boat, and into the water, the boat is top. And because you are here, the extra water, the weight of displaced water is equal to the weight of you. No, nothing to do with the surface area. It doesn't matter. Surface area does not matter. So the thing is, when you're in the boat displaces the amount of water which is exactly equal to the weight of your body. And when you are jumping into the water, it also displaces the amount of water which is exactly equal to the weight of your body. So in both cases, you displace the same amount of water. In both cases, here and here, because you haven't changed, your mass, your weight hasn't changed, you displace same amount of water displaced. So no change in level. Right. There's no change in the water level. And there's a fantastic video about this. Pretty much what I was speaking is on, it's called Physics Girl. And if you search for Physics Girl, she's her name is Diana. She's really good girl. She's unfortunately sick with long COVID right now. And Diana, yeah, so here's the channel, and she has a video about this topic, about the boat. Here you go. Okay. And yeah, so that's about it. Okay, so now we're doing some calculations with forces, and this is my favorite part of hydrostatics, honestly. What mass can a helium balloon lift? Okay, so we have a helium balloon, and we've discussed 2 weeks ago why a helium balloon floats, or why anything floats. So we have a helium balloon, and it usually has some kind of basket, and basically you put something in. And it lifts something. All right. So we know that the volume of the balloon is 10 cubic meters. The density of the air is 1.29 kilogram per cubic meter. The density of helium is 0.18 kilograms per cubic meter. Mass of empty balloon, so mass of balloon plus the basket, is 2.1 kilograms. 2.1 kilograms. So it's a small balloon, not meant for people, but it can lift, I don't know, small objects into some equipment, for example, into the atmosphere. Okay, so how much? So the question is, how much mass can it lift? Okay. So what do we know? Well, we know the upthrust force. We know that the upthrust force is density, gravity times the volume. Okay, so let's look at the forces acting on the balloon. So on the balloon, we have the upthrust force. We have the weight of the balloon. We have the weight of the empty balloon. We have the weight of the helium inside of the balloon. And we have the weight of the mass that is attached. So this is the upthrust force. This is the weight of balloon. This is the weight of helium inside the balloon. And this is the weight of the attached mass. So the upthrust force, we already know, it's density of the air multiplied by gravity times the volume of the balloon. Weight of the balloon. Weight of the balloon is 2.1 times 10. So it's mg, which is 2.1 times 10, which is 21 newtons. Weight of the helium. The helium, weight of the helium, we need the mass of the helium. So mass of the helium times gravity. The mass of the helium is density of helium multiplied by the volume of helium, and gravity is 10 g. So it's the density of helium times the volume times h. So it's the weight of the helium inside. And weight of the attached mass is m1, let's call it m1g. Okay, so we write an equation. This, because in order to be stationary, to be able to lift something, we have density of the air, gravity, volume, equal mg, weight of the balloon, plus weight of the helium, so rho of the helium, GV, and plus m1g, gravity. So we can cancel the g's. We can density of the air, and so density of the air, V, equals mass of the empty balloon plus density of the helium times volume plus m1. So m1 is equal to density of the air times the volume minus density of helium times the volume minus the mass of the balloon itself. We can combine the two, so density of the air minus density of helium multiplied by the volume minus m. Now in physics, Verana, that's a very good question. It would float, yes. But in order to travel upwards with the same speed, well, you need slightly more. But yeah, overall, it's the same. It's the same force. Densities don't multiply; they subtract. Densities, the weight equals multiply with v. So the density times volume is the mass, and density times volume times g is mg, is the weight. And remember, upthrust is equal to the weight. Upthrust is equal to the weight of air, which is equal to rho g v. Okay. So the mass that it can be lifted in physics, we try to write it in an algebraic form, and then we find the final answer. So the m1 that can be lifted is density of the air, so 1.29 minus 0.18 multiplied by the volume, which is 10 cubic meters, minus 2.1 kilograms. So 1.29 minus 0.18, so that's 1.29 minus 0.1. It's embarrassing, but 1.11, so 11.1 minus 2.1, which is 9 kilograms. So the balloon can lift up to 9 kilograms. Of course, if we attach exactly 9 kilograms, it won't travel up. So anything that is less than 9 kilograms is acceptable. But then as the balloon rises, the outside pressure decreases, so the balloon becomes bigger, and the upthrust force increases, so it actually travels up better. Okay. Does that make sense? Does that make sense? How well do you understand this this problem? On a scale of 0 to 10, please. Don't be shy. Right. Okay, so 9s, 5s, and about 2/3 of you have not replied, which is never good. Just shy, but okay. What you need to understand, well, you need to understand that there's an upthrust force, and you need to know how to calculate it. The upthrust force is density times G times V. And then there are forces that are downwards. There's the weight of the balloon, the weight of the helium, and the weight of the attached mass. Then you just, the upwards forces have to equal to the downwards forces. So you just make them equal to each other. That's pretty straightforward. Okay. The next question. What is heavier? Like I did this question 2 weeks ago. What is heavier, a ton of lead or a ton of feathers? Was someone able to figure that one out? I think there was one question. Somebody told me the correct answer last week. Yes, Will. The lead is heavier because there is less upthrust from the air helping you to lift it. Yes, very good, Aisha. Not surface area though, the volume. We don't care about the surface area, it's the volume that matters. More denser, less upthrust. Now, I understand that this is oh, did anyone ask their teacher? Did anyone went up to their teacher and asked that question? Did you get any discussions going on in your class about this? Well, now you know the answer. That's not fun, but okay. So how does it work? Look, if you place anything into any fluid, there is an upthrust force. If you place a brick into water, there is an upthrust force. If you place your phone into water, there will be an upthrust force. And if you if you place a balloon, a helium balloon, into the air, there will be an upthrust force on the balloon. So any object placed into any fluid will have an upthrust force. This upthrust force helps you lift things. If you're in the water, and if you're in the water, if you're not in the water, so a brick in air. There's the weight of the brick. Let's say it's 100 newtons. And there is the upthrust force, which is, let's say, 10 newtons. Oh, sorry, there's no upthrust force. In order to lift a brick, you need 100 newtons of force. Okay, you have a brick. If you want to lift it, you need 100 newtons of force. You need 100 newtons of force. Now, if the same brick is in water, on. If the same brick is in the water, it's going to be 100 newtons. But because there's an upthrust force, let's say 10 newtons upthrust force, you only need to use 90 newtons, because 10 up, you need 90 newtons to lift it, Yes, well, you're correct. Brick in vacuum. Okay, let's put it in brick in vacuum. Now, if you place a brick in air, there will be a tiny bit of upthrust from the air. So this is the lifting force. Lifting force. This is the weight. And this is the upthrust. Now, when you place the brick in water, has an upthrust force. Brick in air also has an upthrust force, but much smaller. It would be like brick in air. Let's do that. Brick in air. It has a teeny weeny upthrust force, maybe 0.001 newton. There's still 100 newtons, but to lift it, you don't need 100 newtons. You need 99.99 newtons. So the air helps you lift things ever so slightly, but it does. Okay? And the upthrust force that helps you lift, the upthrust force is the density of the fluid multiplied by the volume of the object multiplied by the gravity. So because feathers, because a ton of feathers and a ton of lead, they have the same weight. They have the same weight. Let's say, so the weight of 1,000 tons. So that's one. So this is feathers, and this is lead. So it's 10,000 newtons of weight, and this is 10,000 newtons of weight. But the upthrust force on the feathers is the density of the fluid, so the density of air, multiplied by the volume of the object, and the volume times g. So, well, we don't know the volume of the feathers, but because the volume of the feathers is definitely this, so this is the upthrust 1, and this is the upthrust 2. Because the volume of feathers is much bigger than the volume of lead, the upthrust on feathers that help you lift is bigger than the upthrust on the lead. So because you are in a fluid, you are suspended in a fluid, the fluid is called air, then that air helps you lift things. That means you need a smaller force to lift the feathers. So to lift the feathers, let's say the upthrust on the leathers is 1,000 newtons. So that would be you only need 9,000 newtons to lift the feathers. And if the upthrust on lead is, I don't know, 20 newtons, you would need 9,980 newtons to lift the lead. Yes, the upthrust increase with volume. Do you understand? Do you understand problem 5? And do you understand that the answer is lead? Lead is heavier to lift. Because when we say what is heavier, we're not asking for the mass. Yes, mass is obviously the same. They obviously have the same weight. The weight of feathers is the same as the weight of lead. But when we say what is heavier, we mean what is heavier to lift. And lead is heavier to lift because it doesn't have the upthrust force to help you. It doesn't have as much upthrust force to help you lift it. So on a scale of 0 to 10, how well do you understand? So don't be shy. So feathers are more buoyant and therefore they're easier to lift, even though they are both heavier than air, of course. Ooh, that is much better. I like this. I like this much better than the previous problem. Very good. So when you go to school, go to your physics teacher and ask this question and see if it's a difficult one. Like, I mean, I'm sure if I ask this question to, I have 50 tutors, right? So I have 50 teachers that will be teaching you guys, and I train them, and well, I'm sure about half wouldn't know immediately how to answer this question. So it's a tough question, right? So it's a don't you need to mention that it is a trick question. It's a double trick question because, yes, obviously everyone thinks it's a trick question. What is heavier, lead or feathers? They are the same because it's 1 ton. Well, no. If you want to say, what is it? Lead or feathers, right? Tension. What do you mean by tension? Problem 11. Let's have a look. Well, yeah, it is a pulling force. So you pull something out of the water. So for problem 11, you have something in the water and you pull it out with a force. So you have the water level. And because water is not helping you, because the upthrust is equal to rho GV, where V is the volume that is submerged, because the volume decreases as you pull it out, the volume decreases, so the upthrust force decreases. So the tension force has to increase. So that's how you find it. Okay, so I won't go any further than that. It's I think I've given away quite a lot right now. So the upthrust force is this. The tension helps you pull it out, and at some point the rope breaks. A brick is fully submerged in water. How does the Archimedes force change if the atmospheric pressure halves? I love this question, but does anyone know? This is a trick question. So a brick is submerged in water. Upthrust would decrease. So how does that work? Well, I mean, if you don't, if you do the smart thing, and the smart thing when you're doing a physics problem and you don't fully understand it, you go to the formula sheet, right? So if you don't understand how to do a problem, you go to the formula sheet and you look for insights. And the formula sheet tells you that the upthrust force is equal to the density of the liquid multiplied by the volume of the submerged object multiplied by the gravitational force. Which of them changes if the atmospheric pressure changes? Upthrust, Ben, atmospheric is cancelled out. Cancelled out with what? I'm not sure what you mean. Upthrust would decrease. Okay, need an explanation. This would be the same as the atmospheric pressure is included in Archimedes force, so it cancels that. Ooh, will. Yes, going. Yes, that is correct. Less pressure. Look at the force. The upthrust force is density, volume, G. None of them change if pressure changes. Right? So immediately you can guess the answer from here. Okay, obviously that's not enough for the explanation, but immediately you can see none of them change, no change, if the pressure of the atmosphere changes. It's just not a factor. Atmospheric pressure is just not a factor in the upthrust, so no change. Of course, no change. But let's see what actually happens. So we have the atmospheric pressure. Let's call it P0. P0. And the pressure on the top, and as we have already discussed, is H is the height of the water. So that's pressure, the atmospheric pressure plus rho GH. And here, when it's down here, it's H plus A. So the pressure here is P0 plus rho G H plus A. And the cross-sectional area is A. So the cross-sectional area of this one is A. So the force is equal to the force from the bottom. So P0 plus rho G H plus A multiplied by the cross-sectional area A minus P0 plus rho GH multiplied by cross-sectional area A, which gives you, which when you open the brackets, P0 A plus rho G HA plus rho G A minus P0 A minus rho GHA, rho GHA, P0 A, and you're left with rho G A. A is the depth and A is the cross-sectional area, so rho G V. That's it. The force, the upthrust force, does not change. Upthrust force. Upthrust. So if we reduce the pressure to P0 over 2, this reduces to P0 over 2, and this reduces to P0 over 2. And they still cancel out. The pressures cancel out, so there's no change. There's no change whatsoever. Okay, and finally, problem 7. Why is atmospheric pressure measured in millimeters of mercury? Millimeters of mercury. So what does that mean? Well, this is Torricelli's experiment, and he figured out that if you take a tube filled with mercury and you place it upside down, so tube filled with mercury, basically what you do is you fill a tube with mercury, you close the finger, you close it with your finger, you put it upside down into a tub of mercury. This is a tub of mercury. This is a tub of mercury. So you take a very long beaker, so 1 meter beaker, 1 meter beaker, yes, of mercury. You close it you fill it with mercury, you close it at one end, you put it in a tub of mercury, you release the finger, and you hold it with a clamp stand. Okay, so this experiment was done in the 19th century. They didn't care too much about the fact that mercury is toxic. So this is not an experiment I would recommend you doing nowadays. And it's definitely not one of the school experiments that you do. The mercury, so let's Google this, Torricelli experiment. Basically, yeah. So this is it. This is it, and So Dania, is there only option if only doing maths? If you're only doing maths, you can join the follow along group. Okay, follow along group means you don't have a tutor, but you come to webinars, you download the assignments, you do them in your own time. Okay. Would the density of the water be slightly less if the atmospheric pressure halves? Water does not compress, so no. Okay. Water is incompressible, therefore no, it does not affect. I mean, water is compressible, but you need pressures similar to the pressures you have in centers of very large stars. So inconceivably large pressures. I don't know how many marks you need. Last year, we accepted a minimum of 40%. Okay, so 40% and above got 40, no, not 40%, a minimum of 40% in each subject, and then a minimum of 50% average. So you could do 40% physics, 60% maths, and you got accepted. But I can't predict what's going to happen this year. But if you don't want to do, if you want to do only one subject, then you can do follow along without a tutor, with just me. You only see me every week or every other week if you don't want to do physics, and you do the problems in your own time. You can still come and ask questions. So that's fine. Yes, if you join the follow along, you can still attend my webinars. You can watch them, the recordings. You can come and ask questions. I'm happy to talk to you and answer your question. So the Torricelli experiment. So let's what's going on here. So if you take a beaker, a very long beaker of mercury, and you put it upside down into a mercury bath, the mercury will stop at a level of 760 millimeters approximately, and this would be vacuum. So how does that work? Well, if you have a tube, from the bottom, you have the atmospheric pressure, because that atmosphere pushes on the top on the mercury bath, and that means the atmosphere pushes from the bottom. So right here, this is the mercury level. From the bottom, there is the pressure of the atmosphere, P0. There's nothing here. So on the top is the pressure of mercury, and pressure of mercury is equal to rho g h. So the atmospheric pressure is equal to rho g h, and rho is constant, g is constant. So h, the height of mercury, is P0 divided by rho g. And the atmospheric pressure is approximately 101,000 pascals divided by the density of mercury. Density of mercury is 13,000. Oh, that's embarrassing. 13,600, I think. Density of mercury. 13.5? Really? Pretty sure it's 13.6. 34.59. Yes. 13.59 does round to 13.5. Okay, 13.6, so it's 13,600. It's kilograms per cubic meter. And gravity is 9.8. 1. So that is approximately 1 divided by 13,600 divided by 9.81, which gives us 757. So 0.757 meters, which is approximately 757 millimeters. So we measure atmospheric pressure. So if the atmospheric pressure increases, the mercury level increases. So if you have a scale, if you just measure this height, you can measure the atmospheric pressure. The atmospheric pressure increases, the height increases. The atmospheric pressure decreases, the height decreases. This was the first barometer. This is the first barometer that measured the atmospheric pressure. So now we use aneroid barometers without any liquids. They're safer than using mercury barometers. So yeah, that's that. So the height. So atmospheric pressure. So 1 atmosphere is approximately 1001 pascal, 100 pascals, and it's approximately 757 millimeters of mercury, mmgh. So this is another unit of atmospheric pressure. Basically, how high is the column of mercury that can be supported by the atmospheric pressure? Hope that makes sense. I'll stop here. I hope this was useful. We have another week, don't we? Yeah, we'll have another week. So if you have a question about maths, ask me next week, please. What happens if you're good in maths and bad in physics? Depends on how bad you do in physics. Like if you do significantly less than 40% in physics, we think that you wouldn't be able to do the course. So basically, that's where we're coming from. It's not that yeah, well, that's pretty much it. But you're always welcome to join the follow along. I hope I haven't discouraged you to drop. I want to encourage you to do well, and because I mean, physics is fun. It's just like literally the best thing ever. Okay, all right. See you all. Welcome. See you. Thank you.